just realised I actually forgot to start recording that lesson. So if anybody's watching this back as a video, you've just missed the first little bit of the high resolution NMR because I forgot to start recording, but you'll be able to pick it up from all the rest of the examples that we're going to look at. Okay, so we're now done looking at that blue peak. That blue peak is finished. So what we are going to be looking at now is, let's look at one of our other peaks. So let's look at the red peak next. So if we look at the carbon that those red hydrogens are bonded to, we're then going to look at the neighbouring carbons. Okay, it's got to be the neighbouring carbons. So on the right hand side, that carbon's bonded to an oxygen, so we can ignore that. And then on the left hand side, that carbon's bonded to another carbon that has 3 hydrogens attached. So there are 3 hydrogens on the neighbouring carbon. That's 1, 2, and 3 there. So that means we're going to apply the n+1 rule. So n plus 1, n the number of hydrogens on the neighbouring carbons. So there's 3 hydrogens on the neighbouring carbons. So it's going to be 3 plus 1, which means you are going to get 4. So that red peak is going to split into 4 lines. So what I'm going to do is I'm going to split that red peak into 4 lines. Like so. All right. Okay, and then finally we have the green hydrogen. Now, because the green hydrogen is not bonded to a carbon, we just go with there being 0 neighbouring hydrogens because that hydrogen isn't bonded to a carbon, there's no carbon atom next to the carbon that hydrogen's bonded to because it's not bonded to a carbon. So what we do for that particular hydrogen, the green hydrogen, is we say there are 0 carbons or 0 hydrogens on neighbouring carbons, and then we add 1 to that. So that will just give us 1. So that peak is just going to be as 1. Okay, the way that I kind of think about it is the hydrogen that you're looking at, so in this case the green hydrogen, it has to be able to see how many hydrogens are on the neighbouring atoms, and the oxygen here kind of blocks the view from that hydrogen, so the hydrogen can't actually see past the oxygen to see how many hydrogens there are on the neighbouring atoms. So that's why it just goes with there being 0, because it can't see any of them. And that is your high resolution proton NMR for ethanol. Okay. We'll now go on and we'll look at methyl propanoate. So again, we'll draw out our diagram for our methyl propanoate. Oops, that's not right. Let's actually sort that out. There we go, that's better. All right, so we've got our diagram for our methyl propanoate, and again, we shall just highlight our hydrogens that are in different environments, because that's always going to be your go-to move, because it'll tell you how many different peaks you're going to need. So again, I'm just going to keep it similar. Green. All right, so we've got these 3 hydrogens here, which are all attached to the same carbon, which are in the same environment. We'll call that the red environment. We then have these 2 hydrogens here in the same environment, which we'll call the blue environment. And then finally, we have these 3 hydrogens here, all attached to the same carbon, all in their own environment, and we'll call that the green environment. So for this, what I'm just going to do is I'll actually just write out what all the different environments kind of look like for when you're looking at page 16. So we've got, for the red environment, it's basically a CH3 bonded to an O that we're looking for. I'll actually just put it CH3O. For the blue environment, it's CH2. There's going to be an R group on one side and a C double bond O on the other. And then for our green hydrogen, it's a CH3 that's bonded to an R group, with that CH2 being your R group. So when you go and check all of the shifts for those, you get what is in our low resolution. So I'm just going to pop those peaks all in the same place. So we've got these going there. Just going to make sure. Oh, and of course, I've actually, on that first one, I've completely forgot to put in our little reference peak. If I don't do it at the start, I tend to forget. So always a good idea to pop that in at the start. And I'll just pop that in the other diagram as well. Remember that TMS, it's tetramethylsilane, and it always appears at 0 parts per million, and it basically kind of tells you where 0 parts per million would be so that you can gauge the shift from the TMS. Right, so I'm going to draw my green, red and blue peaks with the correct height, and then we're going to look at their splitting. Okay, so we've got 3 carbons in the green environment, so we're going to pop a line in. Mine's is 3 centimeters high on my page. You could have yours 6 centimeters high if you wanted, if you're making 2 centimeters for every hydrogen. Doesn't really matter too much what value you give every hydrogen, as long as you're consistent. Okay. Right, so what we're going to look at now is the number of hydrogens that are attached to neighbouring carbons. So if we start by looking at the red hydrogens, the carbon that the red hydrogens is attached to this oxygen. That oxygen isn't a carbon, therefore there's no hydrogens attached to neighbouring carbons. So we would apply the N+1 as 0 + 1. So that means that that red peak is just going to split into 1, which we already have. By drawing a peak in, you've already drawn 1 in. So the red one, don't need to do anything else to. If we look at the hydrogens in the blue environment, on the left-hand side, we see that the carbon that those hydrogens are bonded to is bonded to a C double bond O, so there's no hydrogens there, so we've got no hydrogens on the carbon neighbour to the left. But then we've also got this carbon neighbour to the right, in which there are 1, 2, 3 hydrogens attached. So what we are going to be doing is applying that N+1 rule for 3 neighbours. So that blue peak is going to split into 4. Which is exactly what we're going to do there. And then finally, we will have our green hydrogens. So looking at the carbon next to the one the green hydrogens are bonded to, which is this one here, we can see there are 1, 2 hydrogens attached to that carbon. So when we apply the N+1 rule, it's going to be N+1, so that's going to be 2 + 1, 2 for the number of hydrogens on the neighbouring carbon. and then that's going to give us 3 in total. So our peak for our green peak is going to split into 3, like so. And that would be your high resolution peak for your methyl propanoate. And then finally, oh, we've actually got a couple extra ones to do here. So we'll look at our ethanoic acid. So we've already done the low resolution for ethanoic acid. So again, I'll just keep the colours the same just to avoid any confusion. Okay, so red and blue. Okay. Right, so we've got 3 hydrogens in the red environment and 1 hydrogen in the blue environment. So just 2 hydrogen environments for ethanoic acid. Looking at our chemical shifts, the blue hydrogen, the one that's directly attached to the kind of carboxyl group, the C double bond O, that was very, very highly shifted. That was having a shift of between 10 and 11, and because our scale only goes up to 10, I'm just going to pop it right on 10. And then for the red hydrogens, it's a CH3 that's bonded to a C double bond O, so that's going to be somewhere between 2 and 2.7. I'm going to kind of pop that in. About there. I'll not forget to pop in my reference peak, my TMS peak. Pop that in right now. And then I'm going to draw the peaks with their correct heights, and then we'll look at any kind of splitting. So there is 1 hydrogen in the blue environment, so that will be our shortest line. And then there are 3 hydrogens in the red environment, so that line should be 3 times the height of the blue line. Now, when we look at the splitting here, if we look at the red hydrogens, this is the carbon that the red hydrogens are bonded to, is bonded to. This carbon that I've just underlined here is not directly bonded to any hydrogens. So for that, when we apply N+1, it's going to be 0 plus 1, which is just going to be 1. So that red peak is going to remain as a single line. When we go on to look at the splitting for the blue hydrogen peak, again, what we can see is that blue hydrogen is directly bonded to an oxygen. So that oxygen is going to block the hydrogen from being able to see what's next door. So we're only ever going to see that as seeing nothing. So we see no neighbouring carbons. So again, that's just going to be a single peak. So for ethanoic acid, your high resolution and your low resolution look exactly the same because the peaks just remain as single peaks. They're not split into multiple peaks. Okay, 2 more examples to have a look at. So what I'm going to do is I'll draw out ethyl ethanoate, and what I would like you to do is to take a minute to see if you can identify how many hydrogen environments there are. And then we'll kind of take it from there. Right, so there's your structure for ethyl ethanoate. Have a look at it. I'll give you a wee minute to see if you can identify how many hydrogen environments there are. Okay, so there are 3 hydrogen environments in ethyl ethanoate. We have these 3 hydrogens here that are all bonded to the same carbon, so they're all automatically in the same environment. And that environment is a CH3. It's bonded to an R group. We then have these 2 hydrogens here bonded to the same carbon, and they are also in the same environment as each other but different to the red hydrogens, and that environment is a CH2 with an R and an O. And then finally we have these 3 hydrogens here that are also in their own environment, and that environment is a CH3 bonded to a C double bond O. So when you go and look at page 16 of your data booklet, you can look at the shifts for all of those. So again, before we forget, we'll pop that TMS peak in. Right, so I'm going to start looking at the red hydrogens. So we're looking for a CH3 just bonded to an R group, and that's the first entry on page 16 of your data booklet between 1.5 and 0.9. So I'm going to pop that in there. So again, I'm just popping in a little marker where I'm going to be drawing that red line, because it's too much to kind of think about where the shifts are going to go and what height the peaks are going to be all at once. So if we work out where the shifts are going to be, we can then focus on the height of the peak. I just find that the most foolproof way of doing this. For the blue hydrogens, we're looking for an R to a CH2 and an O. And if you look at the 4th entry down, you'll see RCH2O, and that's between 3.5 and 3.9. So I'll pop my little blue marker in there. And then finally, I've got the green hydrogens. So that's a CH3 to a C double bond O, which you will see as the 3rd entry in that table, and that's between 2.0 and 2.7. Which I'll pop there. So when we now go on to look at the height of our peaks, there are 3 hydrogens in the green environment, 3 hydrogens in the red environment, and then there's just 2 in the blue environment. So the blue line should be 2/3 of the height of the green and the red line. And for me, it's just easy when I make everything like a particular centimetre. So I'm going to make every hydrogen 1 centimetre. But you guys may choose to use a different number than that. It's absolutely fine. Okay, so what we've got here is our low resolution spectrum for ethyl ethanoate, and what we're now going to do is we're going to turn it into the high resolution spectrum. So that's the best way to do this. Again, just kind of draw out your low resolution and then look at how the peaks are going to split. So let's start with the red hydrogens. So the red hydrogens are bonded to, and I'll call it the red carbon. And we want to look at how many hydrogens there are on carbons that are next to the red carbon. So if we look, we can see that there are 2 hydrogens on the carbon next to the red carbon. So when we apply n+1, that's going to be 2 + 1, which means that peak is going to split into 3. So the red peak will split into 3. Like so. If we then go on to look at the blue carbon, we're going to look at the neighbours to the blue carbon. So on the right-hand side, its neighbour is an oxygen, so we don't look any further than that. And then, sorry, that's the right-hand side. And then on the left-hand side, we have 1, 2, 3 hydrogens that are bonded to the carbon beside the blue carbon. So when we apply n+1, it's 3 neighbouring hydrogens plus 1, which is 4. So the blue peak is going to split into 4. like so. And then finally, if we look at our green hydrogens, let's look at the green carbon. The green carbon is bonded to a C double bond O on the left-hand side. The neighbouring carbon to the green carbon isn't bonded to any hydrogens. So that's going to be 0 plus 1, which is just going to be 1, which means we're just going to see the green peak as a single unsplit peak. So we don't need to do anything with that green peak there. Okay, so our final example for this is going to be methoxyethane. But you know what, just as a wee teaching point, let's change that from methoxyethane to ethoxyethane. And you'll see why we're going to do that in a moment, because we don't have an example that's just quite like this one. Okay, so again, I'm going to give you a minute to see if you can identify the number of hydrogen environments that we have here. So I'll give you a wee minute on that, and then I'll kind of go over the answer, and then we'll look at drawing this spectrum. Okay, so the correct answer for the number of hydrogen environments there are in ethoxyethane is 2. So let's have a look at why that is. So let's start on the left-hand side. So we've got some hydrogens in what we'll call the blue environment. And let's kind of look at what that blue environment is. That blue environment is a CH3. And if we look at what's bonded to that CH3, it's just a CH2. So we would just call that an R group. Remember, R groups are any alkyl groups. So that's any carbon-hydrogen combination. When we look at these two hydrogens here, which I'm going to call the red hydrogens, let's look at their environment. So it's a CH2. Now on the left-hand side, you've got an R group, you've got a CH3, and then on the right-hand side, you've got an oxygen. Now, when you go on to look at the next two hydrogens, what I'm going to do is I'm just going to pop them in yellow, and then I'm going to remove the yellow. So if we look at these two here, if we were to look at the environment that they were in, we would say, all right, okay, well, it's a CH2. Then on the left-hand side, you've got an oxygen, and on the right-hand side, you've got an R group. It's the exact same as the red environment. So what we would do is we would say that those two hydrogens are also in a red environment. And then we see the same thing for the hydrogens that are on the right-hand side. They are in the same environment as the blue hydrogens on the left. We kind of know that hydrogens are going to be in the same environment when the molecule is symmetrical. So there's actually a line of symmetry that runs right down that molecule there. And when a molecule is symmetrical, you're always going to get a lower number of hydrogen environments than you expect So for this one, it's 2 hydrogen environments. So when we go to look at what this spectrum is going to look like, I'm going to start with my TMS peak. And then we're going to look and see where the blue and the red peaks are going to go. So for the blue peak, it's just a CH3 with an R. So that's the first line in the table. So that's going to be between 0.9 and 1.5. So I'm just going to pop a little marker in where that's going to go. And then for our red hydrogens, it's an R, a CH2, and an O. So that's the fourth entry in the table. So that's between 3.5 and 3.9. So next, we need to think about the height of these peaks. So there's 4 hydrogens in total in red environments, and there's 6 in blue environments. So I'm not going to be able to use 1 centimetre to represent every hydrogen here because I don't have enough space to do that. So I'm going to use a 0.5 centimetre to represent every hydrogen here so that I can actually fit it in my page. Just about fit it in my page, like so. Okay. And then what we're going to do is we're going to look at the splitting. So I'm just going to use the left-hand side of the molecule. So if we look at the red carbon, we're going to look and see what it's bonded to. So on the right-hand side, it's bonded to an oxygen, so the carbon can't see anything past that oxygen. And on the left-hand side, it's bonded to a carbon, and that carbon has 3 hydrogens attached. So we're going to use N+1, so there's 3 hydrogens on the neighbouring carbon, so that's going to be 3 + 1, which means that red peak is going to split into 4. So I'll do it like so. And then if we look at the hydrogens in the blue environment, well, they are all bonded to the blue carbon. And the blue carbon has 1 neighbour, and that's the red carbon. And that red carbon has 2 hydrogens attached. So there's 2 hydrogens on the neighbouring carbon. So it's going to be N+1, which will be 2 + 1, which means that blue peak is going to split into 3. Like so. And that would be your high resolution spectrum for ethoxyethane. Okay. Right, so just to finish off, we will very quickly look at the last page in this booklet, which is just on UV spectroscopy, which we don't actually tend to look at an awful lot in comparison to the other 3. So we'll just kind of talk through this. So with ultraviolet and visible spectroscopy, it says, while some organic molecules are coloured, and that's due to conjugated systems lowering the energy gap between the highest occupied molecular orbital and the lowest unoccupied molecular orbital, most appear colourless. So it's not common that organic molecules have that conjugated system, so most organic molecules are going to be colourless. And colourless organic molecules are colourless as the energy gap between the HOMO and the LUMO is within the high energy ultraviolet region of the electromagnetic spectrum. And that's all we're kind of doing there. So that just serves as like a little recap from the end of the molecular orbitals booklet that talks about conjugated systems in your HOMO and your LUMO and the possible electron transitions within that. So I'm going to stop the recording of the lesson just now.